Okay, all right. So now we have the second lecture from Irene. Thank you very much, Irene.
Okay, welcome back. So today is day 2. So we will talk about instruments and in particular gravitational wave interferometers. So let's recap a bit what we talked about yesterday, and then we go on. Hopefully I will start a bit. I will stop a bit earlier, so we have as usual few minutes for question. But feel free to stop me anytime you feel the urge to ask a question. So yesterday we have seen this the first binary black hole detections. But you couldn't hear the chirp. I want to try once again. Let's see if we are lucky today. You hearing something? Is it on? Sorry. Okay. Now the mic should be on. You hear anything? Okay. So that was the chirp. Whoop. Of the signal. Let me turn it off. Okay. So yesterday, I've seen that this, well, actually, we didn't see. We just talked about it as a huge success in the detection of gravitational waves. So this binary system composed of two black holes. Is composed of a black hole of 36 solar masses and another one of 29 with a diameter that are few hundred kilometers. And this event happened, give or take, 1.3 billion years ago. And the impressive energy that this system releases, it's order of 3 solar masses in the gravitational wave effect. So it's what we actually detected in the detector. And so it was brighter than everything that we have seen in the universe. I want to show you what really happened. So you see these two compact objects spiraling each other, and then this wave that you see are the gravitational waves that they travel through the universe, galaxies, star, dust, whatever it's around, and then they arrive to Earth. And as you see, the effect is extremely exaggerated, and what you see is the squeeze and shrink of our planet, and that's the key point. So what happened in the detector? So we said that there is the laser, that the laser beam is split into the two arms, in the two perpendicular arms. When there is no gravitational wave, the outcome on the photo detector is null because there is the perfect coincidence, and so they cancel each other. If there is the passage of the gravitational waves, you have seen that the end mirror moves, and so what you have is a constructive interference that will end up in light in the photo detectors. That's pretty simple. Let's see. So yesterday we just come around starting from the Eisenfield equation. We consider the weak field approximation, and we said that the wave equation for the metric tensor, for the tiny metric tensor, is this one. And so the solution with two independent polarization, H cross and H plus, are this one. And you see again the effect on the human being, of course, largely exaggerated as in the previous video. And the other thing that we just flashed out was the fact that in our detector, what you have is a time series, and you can write that as the combination of the two polarizations that are convoluted with the antenna pattern plus the noise contribution. And what we will see in the following slide will be extensive noise curve, so sensitivity curve, if you prefer, of the detector that are not other than the power spectral density of the amplitude. And so the other thing that we considered yesterday was the fact that the most effective data analysis tool that we can consider is the match filtering. But we have seen that as every in real life, it doesn't work as perfect as we would like. We have to do some work with the data, remove glitches, no noise, to make it work even better. Okay, so let's start from the beginning. I will start with a bit of history because so that you have the timeline in place for this type of detector and how many years it takes from the starting point to the actual discovery of the gravitational wave. So in the beginning, we start with Ray Weiss that you see in the upper right corner, a really young Ray Weiss. In the 60s, it was giving a course of general relativity at MIT. And he worked and he wanted to give to the students um, not usual homework to do at home. And so what he did was to propose how it would work at a laser interferometer detector to detect gravitational waves. And so that was the initial idea and the beginning of the story that brought us till here today. So this is the timeline. So as you see, the apart from the homework, the actual feasibility study started around 1970 for these laser interferometer gravitational wave detectors. And then what you do is you do a feasibility study and you go to the agency. In this case, was US, so it can be either the DOE, the Department of Energy, or the NSF, so the National Science Foundation, and you ask for funds. Fortunately, they give the funds to the two important labs. So one is at the MIT and one is at Caltech on the other side of the country. And they started the development and the R&D studies for the construction of the detector. And you see the construction proposal for LIGO was submitted, and that was the amount of million that was foreseen to the construction of the detector, $365 million. And that was 2002. Then the cost increased exponentially, so probably arrived to order of billion. So what you have is from the 70, then you have to arrive to 1994 for the first groundbreaking at the Hanford site. And then that was just the beginning because apart from Hanford, there was the first detector. Then there is also the Livingston one on the other side of the country. And you see, this is there was another proposal after the first scientific operation that ran for the 3 interferometer that we will see in a second. And then this other proposal, it was a joint effort between UK, Germany, and US. And then in 2000, no, in 2014, there was the starting scientific run for engineering run, sorry, of only 2-hour lock for LIGO, and we are talking about already an upgraded detector in comparison with the initial LIGO, as we used to call, and then that we arrived to September 2015, in which there was the first operation and also the first detection, likely. Here you see other interesting people that were involved in the in the project and also in the characterization of the astrophysical sources, as in the case of Kip Thorne. Of course, this was uh, uh, this was the history for LIGO. A similar history went down for Virgo. It took about 30 years to build a reasonable detector, reasonable in the sense to be sensitive enough to a certain kind of astrophysical sources, and then another 10 probably to be able to fine tune the instrument and arrive to these amazing detections. Here you see just a few of the runs that were going between 2002 and 2007. So initially, the LIGO and Virgo collaboration were separated. They didn't join data, and then they realized that putting the effort together and solve together the same issue that they can have with similar instrument could be something really useful for both collaboration. And so we don't only share data, but we also share the knowledge of how to solve the issue that we find in the detector that can be relevant also to the other one. Okay, this is um, the advanced gravitational wave detector network. So you see, we have two advanced LIGO detector in the US. One is in Hanford and the other one is in Livingston. The arm length for each of these detector is 4 kilometers. Then there is Virgo in Cascina, nearby Pisa in Italy. That is bless you. That is a 3 kilometer arm length interferometer. Then in Germany, nearby Hanover, there is the Geo 600. 600 because the arm length of this detector is exactly 600 meters. And so it's not compared, cannot be compared with the sensitivity of advanced LIGO and Virgo, but it can be extremely interesting to have this data to refine the astrophysical object that we are going to locate. Then there is CAGRA, that is considered a 2.5 generation interferometer, so is a bit more advanced that that advanced LIGO and Virgo in the sense that is already underground. It's exactly the same concept, but is underground. Is in the Kamioka mine, where also Camio Grande was. And the arm length is the same of Virgo, so it's 3 kilometers in length. And then there will be LIGO India that was approved, probably. So there should be a twin of the LIGO detector. So it's supposed to have a 4 kilometer arm length with exactly the same characteristic of the advanced LIGO detectors. And I think the site has been chosen, but they didn't start the construction yet. So of course they will go a bit faster due to all the knowledge that we already have, and so we will support the construction of these other instruments to enlarge the network of the gravitational wave interferometers. So let's start with the LIGO detectors. At the beginning, there were three LIGO detectors. Two were co-located in Hanford, as you can see here. One was a 4 kilometer arm length, and the other one was a 2 kilometer arm length, with exactly the same orientation. While the one in Livingston is a 4 kilometer length. So the two detectors were the two co-located detectors were in operation for about 10 years. So till the advanced detector, because it wasn't feasible to upgrade both detectors at the same time in the same location. So the NSF decided that a bigger detector would be upgraded and sensitive enough to look for astrophysical sources. And note that yesterday we considered the time delay between the two light detectors. So to cover about 3,000 kilometers, the light that travels between one detector and the other takes about 10 milliseconds. So keep this in mind, because uh, uh, we need this information when we make the coincidence of the data, and also to remove artifacts in the data. Uh, of course, as in every detector, there were some difficulties, so flooding, fire, people driving crazy around, literally. And so, apart from these, animals everywhere. Apart from these, we we managed to start the run in 2002. Um, Similar story. Virgo had a similar story. So instead of having Ray Weiss, we had Adalberto Giazzotto, that was the driver of the Virgo collaboration and also the construction of the detector. As I told you, this detector is 3 kilometer arm length, and has been proposed in 1989, and it started the operation at the construction between 96 and 2003, and then it was in operation with the LIGO detectors. The estimate of the cost is about $20 million. Just Virgo, not the upgrade. That's the initial Virgo, as in the other case was the initial LIGO. So how does an interferometer work? We have seen that gravitational waves are ripple in the space-time, and they twist the space-time. And so what you have to detect is the slightly motion of the mirror that are at the end of each of the perpendicular arms that compose your detector. And if there is a gravitational wave passing by, you will see the light on the photodetectors. Otherwise, you don't see anything. So it's completely blacked out. And this H that we have seen in the equation yesterday is none other than the displacement of the mirror that you detect, that is this delta L, over L, that is the length, the actual length of the arm. So this is, now we will see this L, we have seen that is either 4 kilometer or 3 kilometer in the case of Virgo and Cagra. It's a bit more complicated than this. So I will show you different optical layout of each of the interferometer. But the key point is the fact that what you are trying to do is to make an extremely precise measurement. And so what you have to reduce as much as you can are the known source of noise. That's the reason why when you look at the sensitivity curve, you have to consider that you are looking at the noise of the detector. And so what you have to do is think, what can I improve? What kind um, of trick I can think of to reduce the bulk of the noise at that particular frequency. And so as you can imagine, the control an interferometer, and so put it in a data acquisition mode, that is lock the interferometer. It's a really complicated um, activity, in the sense that you have to have under control not only the electronics, but also the optics, the laser, the mirror, and so on. And all the mechanics has to be in place and work perfectly. Um, Yesterday, we introduced the knowledge of the antenna pattern, and what I told you is that this response of the detector depends on the position of the source that you want to detect, and also on the orientation of the arms that that are the principal component of your detector. And so when you detect the displacement of the mirror at the far end of the arm, what you also have is a displacement in the phase of the light that recombines on the photodetector. And so here you have an example at the bottom right of the slide of what is the simulated antenna pattern for the plus polarization and the cross polarization, and also the total of the two. So when it's totally unpolarized, so you see that if you are not looking for a specific polarization, you lose sensitivity in almost every direction. So you have to be careful on what you consider. And just for clarification, um, so what the coordinate system that you use to make this type of exercise is the following. So you consider the beam splitter, so the mirror that divides the laser beam into two in the arms of the detectors as the origin of your system. The two arms are the x and y axis, and then and so they live in a plane, and then what you see is the source that is right here. And this source not only has a polarization angle that is due to the waveform that is coming at you, at the detector, but also can be identified through the two polar angles, theta and phi. Okay, so I want you to know something, to note something. So we said that to compute H, so the strain that we desperate want to see, we need to be extremely sensitive. How sensitive? So if we want to get an H that is a level of equal or less than 10 to minus 22, considering an arm length of 4 kilometer, that means that we have to detect the displacement of the mirror that is 4 times 10 to minus 19. Remember that the diameter of a proton is 10 to minus 15 meters. So we are going much less with that. And the other thing that is interesting is the fact that in this configuration that is still a simplified configuration for the interferometer, you see that the mirrors are suspended. Why are they suspended? So we want to have the mirror in the so-called free fall mode. So this way, we try not to get rid of part of the seismic noise that propagates to the motion of the Earth and to the diffused silica fibers that keep this mirror in the more or less free fall condition. Okay. Um, so in the noise bulk of the detector, that see there are three main noise contribution. So we have the seismic motion that is below 10 hertz, more or less, so really low frequencies. That's due to earthquake or motion, anthropogenic motion of people around the detector. Then in the bulk of the sensitivity, we have the thermal noise, and so the vibration due to the temperature that we have inside the detector. And in the upper end of this noise contribution, we have the so-called shot noise. The shot noise is the quantum fluctuation in the number of photons that we detect. So let's as I said, you can have different classes of detector of noise. So the anthropogenic noise, the earthquakes, radio frequency. Yesterday we see this blip when I show you the gravity spy, in which you can uh, classify the different kind of noise. and also correlated noise that could be due to electromagnetic noise in the detector due to solar wind or particular kind of events. Um, this is just to show you that it's important to understand what's going on in your detector, because when you have to analyze the data, you go through a calibration process plus a data quality process, in the sense that you have to veto that particular part of the time frequency in which you see a noise that either is well known or you don't understand at all, but for sure will be problematic when you apply the match filtering. And so here, for example, this is the example of the trigger rate over the coherent network SNR for the GW150914, so the first ever gravitational wave event. So you see different type of categories. Category one is just the first one, the rough check that you do to remove the known artifacts, and then you go through and you check carefully what else you need to remove, and so you arrive to category 3. And so the yellow curve is what is left. Okay. So few picture of LIGO. Again, this is the instrumental hole where there is the beam splitter, and that's the beginning of the mirror at the beginning of the two arms. These are some attenuator to remove the transition of seismic noise from the ground to the mirror. It is a scientist that is working with the mirror mass. Okay, so as I told you, it's pretty complicated and chaotic if you're not used to it when the layout of an interferometer shows up. Here you have the different, so here you have this one is the beam splitter, and these one are the two arms. So with the starting mirror and the end mirror for each of the arms, and the laser is here. So between this point, the input point, and the beam splitter, there is the input Mach linear that keeps the frequency and the power of the laser in place and more or less stable. And then there are other tricks that are used to maintain also the number of photons that have been produced. This is an example of an optic table in which you pre-stabilize the laser, and so is just before the laser will input something inside the cavity arm. And this is the work done at the Max Planck in Hanover, and this one is one of the test table in which they tested this pre-stabilizing laser. The other interesting thing is the fact that when you think about the masses, and so the mirrors that are inside the detector, they are not just mirror. They are mirror that have specific characteristics, not only due to the fact that they have to be 99.99999% refractive due to the fact that you don't have to lose the signal, but also on top of this, of each of these mirrors, there is a coating that is like a tiny film that you apply on the surface of the mirror to make it even more sensible and even more reliable for this type of instruments. And so you see, this can be um, uh, this could be also problematic in the sense that the coding, as you see in this picture, it doesn't always work at its best condition. So you see that the coloring of this mirror is not equally distributed. So that means that when you have a laser that comes with the photons that will make pressure on the mirror, and so the mirror will move and will activate the vibration modes, this one will not move in a monolithic sense, but there will be vibrational modes inside the mirror that will impact also the detection that you are trying to make. These are other pictures from the advanced LIGO installation. So you see that's the optical table. That's one of the mirror that is going down in a really uncomfortable way. So we started with a really simplified Michelson interferometer. That's how it's called it. And this one is one step ahead. So it's what was the layout for the detector that we have in place. This is another view of the instrumental hall in which here you have the laser, here you have the photo detector, and here you have the starting of the arms. So when we consider the sketch, the layout of the LIGO and Virgo interferometer, what you have seen are two recycling mirrors. So one is called a signal recycling mirror that's at the output to enhance the sensibility of a particular frequency. So it's here. Here there is the photo detector in which you want to see the light. And here, instead, there is the so-called power recycling mirror that is at the input of the detector to increase the, the laser intensity in the arm. Another thing that is peculiar in this type of detector is the fact that they use Fabry-Perot cavities here and here, so along the arm of the detector. These cavities are linear optical cavity that allow the reflection of the mirror to be better. And so the light bounces back and forth several times before going back to the beam splitter. And what is important in this case is the finesse, the so-called finesse of the Fabry-Perot cavity that allows this bounce back and forth to be multiplied by a factor of 100. So here you see that the mirrors are not only suspended, but they are, and so as we said before, in free fall, almost free fall. There are some kind of attenuator on top of it. That's to reduce not only the vibration coming from the motion of the earth, but also the thermal noise. So here there is a comparison. So this is the sensitivity curve of an interferometer. On the vertical axis, you have the strain noise, H, and you see it's 1 over square root of Hertz. And here you have the frequency. So this curve is the noise budget or the sensitivity curve for initial LIGO. And so what you see is that the sensitivity is often converted in the detection horizon that you can reach for a particular kind of source. So in this case, the detection horizon is computed for a binary neutral star system. So what you do is you consider a binary neutral star system and you say, how far can I go to obtain this type of source, the detection of this type of source, in a way that I have in each interferometer an SNR of 8 on the noise level. And that's about, for the initial LIGO, was about 15, 20 megaparsec. So if you have a source as a binary neutral star that is in that range, you could say that you we are able to detect that type of source in that detection horizon. And you see there is a factor of 10 between the initial LIGO and the advanced one. So now we will see what we managed to do to increase the sensitivity so much. Because increasing the sensitivity of a factor of 10 means that what you get is an horizon that is order of 200 megaparsec with the same binary neutral star system that you want to have. So as we were saying before, the noise spectrum of the detector is roughly divided into three areas. So at the low frequency, below 10 hertz, what you have is the seismic noise. It's this pinkish box. This one in the light blue area is the most sensitive part of the detector that we call bucket, and it arrives to about 300 hertz. And that's limited by the thermal noise. Instead, this one, the green one, is the one that is limited by the shot noise. So the number of photons that we can detect. So for the seismic noise, we said that is due to the ground motion of Earth that can be coupled with the movement of the mirrors. And so the solution is to suspend the mirror and try to have a stage of several composed pendulums to reduce the amount of vibration that will go actually into the mirror. For the thermal noise, it's a bit trickier in the sense that you know that that's a combination of normal modes of the mirror and the vibration of the suspension. So each of these has an energy fluctuation that depends on the temperature times the Boltzmann constant. And so the only possibility that you can have is to act on the temperature. And so what you do is you use cryogenic solution. And so the arm of the detector not only are in a Fabry-Perot cavity, but that's in a cryogenic environment. For the shot noise, what you have is the fluctuation in the number of photons we said, and you see that's inversely proportional to the length of the arms, this L, and this one P is the input power. So if you increase the length of each arm of the detector and or you increase the input power of the laser, you solve the issue, apparently. So let's see what happened. Let's try. So here you have a again, the plot is exactly the same. So you have the strain in the vertical axis over frequency in hertz. The blue curve is the one that is showing you the so-called radiation pressure noise. That is the quantum fluctuation of the light that is transferred to the mirror, and you see that goes as goes inversely with the mass, and it's proportional to the square root of the input power of the laser. And instead, the orange red curve is the one that is showing you the shot noise that we said is inversely proportional to the square of the length of the arms and the input power. So let's try. So the combination of the two will be for the lower frequency will be this blue part. For the highest frequency will be this part. So let's try to keep the mass at the same amount and increase the input power of the laser. So what we should see is that this part of the curve, the shot noise goes down. So we are actually reducing the shot noise. But at the same time, this part will be worse, so it has to move in the right direction. Okay, so let's see. This is the noise budget that we have with the combination of the two. You see the mass is 40 kilograms and the input power is 10 to 3 watt. What happen if we increase the power of a factor of 100? So you see that was the blue and that was the yellow. So we decrease the shot noise, but the radiation pressure is even worse and gets even worse when we consider the input power to be 10 to 7 watts and the mass is still stable. So what you have to do is try to find a balance between these different noise budget and try to find a reasonable way to reduce the intrinsic characteristic of this sensitivity curve. So how do we do it? So how do we go from initial LIGO to advanced LIGO and we gain a factor of 10? So for the seismic noise, what we can do is to suspend the masses through several stages and so be able to isolate the system from the rest of the instrument. And so in this way, we gain this much at really low frequency range. Then we have to reduce the thermal noise or the Brownian noise, sorry. And so the way we do it is to use monolithic suspension. And we try to improve the thermal noise in the bucket, so in the most sensible region of our instrument. For the shot noise, what we do is to increase the input power and include the signal extraction cavity, so to make sure that the count of the photons is really under control. A similar, so till now I've speak about LIGO. The similar layout that we have a similar layout for Virgo and advanced Virgo. The only key difference in the case of Virgo was the use of this object over here to suspend the mirror. This one is called super attenuator and it's composed of several stages of pendulum that are actively trying to remove the seismic vibration of the Earth, and so avoid that this vibration can go through the fibers and also the mirror. So also in the case of Virgo, there was an increase in the sensitivity curve of about a factor of 10. So also an increase that mirrors to the increase in the detection range that you can gain. In the case of Virgo, what was improved was the optical configuration, to have low mechanical losses. We use fused silica fibers, so a different kind of fibers, and a different combination of coding for the mirrors. And to put down the shot noise, the input laser was the input power of the laser was increased. We also consider a higher finesse for the cavity, and the optical configuration was slightly changed. So this is the figure of merit that you have of the different stages of the evolution of these interferometers. And so you have in blue, in violet, the early configuration, in green the middle one, the late one, and the sign sensitivity. And what you have always is this the volume at which you are sensitive in the case of a binary neutron star coalescence. So you consider the two binary neutron star of 1.4 solar masses and you consider the fact that you have to detect this type of signal with a signal to noise ratio in each detector that is equal to 8. And so in this case, for the advanced LIGO evolution, we should be able to arrive to 200 megaparsec. In the case of Virgo, it's 150. Remember that there is the arms are not the same. So Virgo is particularly well behaving, and this is what is the expected amount of signals that we should get. Of course, you see the time scale is completely not today, in the sense that right now we should have already the LIGO India detector in place, but it's not the case. So we are a few years behind schedule. But apart from that, the 200 megaparsec range for the binary neutron star is still there. And so that will be the goal to start the O4 scientific run. So I want to show you how tiny can be these 10 to minus 21 or 22 that we want to detect. So in the case we want DL over L, that is 10 to minus 21, that is 1 over 10 to 21. That means this number, that is impressive. And so if you consider the solar system, you divide by 1,000, you have roughly the size of our Earth. Then you divide again, and you have the size of Sardinia. Actually, Scorpio. Sorry, my mistake. That's that's the dome in Florence, and then you divide it. You have the size of a hand. Then you have the size of a human hair, and then you have bacteria that unfortunately we know it already. And then you have the size of an atom, but we are not still there because, you know, I compared before with the diameter of a proton that is 10 to minus 15 meter, and so we need to push a bit more to get to the result that we want. So right now, to sum up, I want to show you this. Is short, it's just a couple of minutes, but summarize what we said till now. Let's see if it works.
In an interferometer, a laser beam is split into two beams. Mirrors reflect the beams, so they meet again at the starting point. If now the distance to each mirror is exactly the same, no light will be seen by the detector. The waves of one beam extinguish those of the other beam. This is called interference. The gravitational wave distorts space. One arm slightly shorter and the other arm a little longer. Light waves do not cancel each other anymore, and we now measure a tiny signal in the detector. Now we add an extra mirror in both beams. In this configuration, the beams bounce hundreds of times back and forth between two mirrors before returning to the beam split. The intensity of the light in these so-called Fabry-Perot cavities increases substantially. The cavities boost the interference effect a few hundred times. The sensitivity is further increased with two additional mirrors, which recycle the outgoing light into the cavities, and with a so-called mode cleaner, which removes disturbing noise from the laser beam. The light power in the cavities is increased to hundreds of kilowatts. Even more complex optics and electronics are required in order to keep the mirrors properly aligned and in position. Ground vibrations at about 100 nanometers are nevertheless millions of times greater than the vibration caused by a gravitational wave. Therefore, all components are mounted on horizontal and vertical vibration attenuators, the best in the world. While the ground is trembling, the mirrors and beams feel nothing of it, thanks to the super attenuators. Also, air presents a problem. It gives rise to unwanted vibrations, such as due to sound. Four so-called cryogenic traps provide an ultra-high vacuum quality. We can pick up hundreds of times more signal of a gravitational wave by extending the Fabry-Perot cavities to 3 kilometers. This and much more is needed to realize an interferometer for detection of gravitational waves.
All right, so that was a summary for the detector. So we now know almost everything about the detector. So when we have three detectors in place, as we discussed yesterday, we can perfectly, almost perfectly, uh, according to error regions, um, identify the source that is producing your signal. This error region that is associated with the detection that we have will decrease in area when we add more and more detector of the same kind, the same sensitivity network. So the localization of the source is done by triangulation, and so you take two pair, take three pairs actually. Each pair localize on the sky. And when they find a common point, that's the localization of the source. What you have to remember is that the travel time between the two LIGO detectors is 10 milliseconds. Between the LIGO detectors and Virgo is about 27 milliseconds. And so taking this into account to make the coincidence of the time series, you can easily pinpoint the location of the source in the sky. I want to show you what the sky localization looks like when we add other interferometer to the network. So here we have the early stage of the interferometer, in which you have only M, Piston, and Virgo, their initial configuration. So you see these elongated shapes are exactly the error region that you expect if a source, if you localize a source at that point in the sky, and so you have order of 1,000 square degrees in the sky. That is crazy when you want to follow up that event with telescope that required an error that is 0.1 degree. And so what they've done, especially starting with the first detection, was to divide the error region in different sections and span a few of them with the different telescope that we have in place for the follow-up. And the red cross that you see are the places in which this network is completely blind. So if something happens there, probably we will not be able to localize it. What happened when we upgrade the design? So you see there is these to these. There is a slight increase in size of these blue contoured area that you see. But still, so that's what you have seen is that what is just we pointed out before is the fact that you pass from a detection horizon of a binary neutron star that is the 80 megaparsec this network to double the same amount. So you are seeing things that are further away, twice the distance that was in the previous configuration. What happened if we add Livingston, LIGO India to the network? That would happen. So you see, you pass from 100 square degrees to tens of square degrees. It's not yet ideal, but still is a huge improvement in the association of the error region with the position of the sky that that you want to see. Okay, so these are the detector that we have right now: Advanced LIGO at Hanford, Advanced LIGO on Livingston, Cagra, and Advanced Virgo. As I told you yesterday, the fourth observing run started 24th of May, so a few days ago. So we hope to have even better detections with the increased sensitivity that we achieve. This is the prospect of what is uh, the effective distance in which we can detect binary system in LIGO and Virgo. So you see at this point, 04, so the expected range for LIGO is between 160 and 190 megaparsec. For Virgo is between 90 and 120. Will be further improved in the O5 for us is like the design sensitivity, so it will be the best possible achievement that we can get. So in the case of LIGO will be 330 megaparsec. In the case of Virgo will be between 150 and 260 megaparsec. And that's to give you an idea of. So that's on the right. You have the same information, so in a different way. So you have L1 and 2. You have O1, O2, O3. So the three different observing run that we had previous to the one that just started. And here you have the um, the total duration sensitive distance for the detector. So here the green is Livingston in this case, and the red is Hanford. During the first observing run between 2015 and January 2016, only the two LIGO detectors were in operation. Then we have the second observing run that was between November 2016 to August 2017. And in that case, we joined in the last month, just in time to see the fantastic discovery of the binary neutron star. And then the third observing run was between April 2019 and March 2020. And again, the three detectors were in operation, and also Cagra managed to join in the last part in the last part of the run. And here you see how yeah, you see the sensitivity curves in the different runs, O1, O2, O3, are slightly different, especially in the lower frequency part. So here you see that there was some effective noise decrease in below 100 hertz. So what's the timeline? So we are in 2023. We just started 04, so we have to shift this a bit more. And we expected to have a 20-month run for 04. And then there will be another upgrade of the detectors, and then it will start 05. That should be the best. I mean, we should be able to reach the the layout sensitivity that we always wanted. What do we have to expect in terms of these actions? It sounds thrilling in the sense that combining the three previous observing rounds, we had 90 detection. We expect even more, about 174. And so we are waiting to improve our sensitivity to be able to obtain information for the post-merger of the binary neutron star system, and also obtain information about some critical part of the waveform, like the ring down part that we were talking about yesterday. And you see uh, the, the detection horizon is about 190 megaparsec for a binary neutron star system in H1 and L1, and it will be about 90-100 megaparsec for Virgo. What is the future? So of course we want to have better detector, longer detectors. We use new technologies, and so this this part to the future is bringing us to discuss about two different instruments, Einstein Telescope and Cosmic Explorer. One is an European effort, and the other one is a US effort, as usual. So and of course we should have, as we talked briefly in advance, also LIGO India in place. So LIGO India will be a twin of the LIGO detector, so will be exactly the same technology, 4-kilometer arm length, and that's it. For the future, so we are talking about R&D process and try to find the best way to actually build these detectors. So the idea for Einstein Telescope is to have a triangular shape underground. So that would be composed of three different detectors. One that is more sensitive to the really low frequency end of the spectrum. Another one will be more sensitive to the high frequency part of the spectrum. And the fact that we will have these three detectors in the same place will allow us to locate the position of the source just with this detector. If the design remains like this, it will be underground, and each arm will be 10 kilometers in length. In the case of Cosmic Explorer, there is a bit more of discussion. So the first proposal was to have a detector with the same technology as the LIGO detectors, but with the arms that are much longer, so order of 40 kilometers. What they are discussing right now is to have two detectors, both with the same technology of the LIGO detectors, but with the arms of 20 kilometers, or one of 40 kilometers and one of 20 kilometers in arm length. So there is still discussion in this sense, as there is in the case of Einstein Telescope, the design, the triangular design with the 10-kilometer arm length has been approved by the European Commission. So for that, that's another step that Cosmic Explorer has still to pass in the phase of the NSF or DOE that will fund the experiment. Where do we want to have this 3G detector, so the third generation detector of gravitational waves? Because we want to go to lower frequencies, and so to obtain the subtraction of the Newtonian noise. We want to have better and bigger laser performing at the other end of the line. So towards the high frequencies. Um, and we want to use cryogenic mass and different kind of suspension, vector coding. And so you see this diagram, it goes in every direction, and of course the gain is proportional with the complexity of the instrument that you want to build. These are um, some of the expected behavior for Cosmic Explorer and ICE telescope. So here you see the strain in the vertical axis over frequency, as we have seen many plot in this last hour. So here you have the sensitivity curve of advanced LIGO. And here you see there is a huge increase both in the case of Einstein telescope and Cosmic Explorer. And the reach that you can gain in redshift is really huge. So you can arrive to a redshift at its order of 100. So you can also reveal merging black hole propagation to the first moment of the universe. That's really, really interesting physics to make. So the Einstein collaboration is already formed. As you probably know, there is also a Brazilian group here. There is Ricardo, that is one of the component is the leader of the group. And of course, we are in the Einstein collaboration. They are discussing during the R&D phase, which you actually test what you would like to do, and then you decide to go for one configuration instead of the other one. And this is the attempted noise bulk that you will have in the Einstein telescope with the different configuration. What you see, LF is low frequency detector, HF is the high frequency detector, and this one, the dark red one, is the combination of the two. So in that case, you will be able to reduce the seismic noise and also a bit of the shot noise over here, and so you will have this complicated sensitivity curve. What about the site? So at the moment, there are two candidates. One is in Linzburg, that is a place between Netherlands, Belgium, and Germany. And the other one is in Sardinia, in Italy. So one is over here, and one is here. The place, the site for the Einstein telescope hasn't been decided yet. The time scale should be next year. So next year we should be able to know where it will be located. There are already a lot of effort, not only in Netherlands and in Germany, but also in Italy, to for the preliminary qualification of the site. So the study of the seismic movement of the ground, and also build a proper prototype to be used in tests that we can use in the cryogenic temperature, and so be able to decide where to put the detector. On the other side of the ocean, Cosmic Explorer is in about the same position. They are in R&D phase. They wrote the white paper on the in which they describe how they envision the instrument, what type of science they want to achieve. In this document, there is still this 40-kilometer detector per site. So you have to find a location, as in the case of the ICE telescope, that is hasn't been decided yet. And as we have seen just before, with this 3G technology, you can reach a redshift of 100, and this means be able to the detection not only the population of binary black hole that are around 3 or 5 in redshift, but also this other population of binary neutron star. And here is the layout of the sensitivity curve. So the strain over frequency again. This is the advanced LIGO. This is LIGO plus that will be 05 most probably, and this is the gain that they can get with this detector. So the idea is to target to arrive at a sensitivity that is better than 10 to minus 24 square root of hertz in a frequency range between 1 and 4 kilohertz. So these are the main science goal: extreme gravity, extreme matter, observation of primary stellar black hole throughout the universe, and of course cosmology and early history of the universe, since we can push the redshift to a great level of Z equal 100, and so we can really study and reveal the fundamental properties of the black hole. What is the global timeline? In the two cases, the conceptual design has been done. In the case of the Cosmic Explorer, there is a white paper. In the case of Einstein telescope, the Einstein telescope proposal is in the speed roadmap. That means that there is the first approval from the European community to fulfill and be able to build this detector. And then the more urgent question is the site localization, so the selection of the different sites, and then there will be the financial issue and so on, the approval of the different governments. What is the message? The take-home message is that we have already these impressive detectors, and we are hoping to do even better, and so to observe gravitational waves through cosmic history. So this is my last slide. I will take any question that you have.
Okay, questions.
Okay, thank you very much for the nice lecture. So I'd like to know why in the noise sensitivity curves we have all those spikes.
So the spikes that you see are the comb that I was telling you about yesterday. These are vibration mode of the mirrors. There are other particular frequencies of 60 hertz, 120 hertz, and they are things that we know they are there, but we cannot avoid, so they are still there. So we clean for these type of modes.
Hello, thank you for the lecture. I have two questions. The first is on the same direction of about the noise. I'd like to know if that's possible to reduce the noise using computational tools, something like that, learning maybe.
Computational tools.
Yeah.
Sure. One of the, yes, you have, the short answer is yes. What you do is you don't do it on the instrument, you do it afterward when you see the data, but that's one of the things that we do most commonly in our pipeline to compute the different calculations. So it's both an effort in the classification of the noise plus the data quality that I showed you before. That's done usually with machine learning algorithm that recognize the feature that we already know.
Okay. The second question is, so we we observe the gravitational wave because the space-time stretch the arms of the detector. So what's happened if the wave come on the plane of the detector?
You see another type of signature that you can reconstruct. If it's the exact plane of the detector in one case, it will not be the same for the other two detectors. And so you will have anyway the possibility of reconstruct the waveform and know where the source is located.
Okay, thank you very much.
Who was next? Okay. By the way, I vote for Sardinia.
Thanks. We hope to.
Hi, thank you for the lecture. When you're showing the comparison between initial LIGO and advanced LIGO, the strain noise from initial LIGO and advanced LIGO, the place where we had worse noise control was the thermal gap, the thermal noise. And my question is, why is that? Like the region
You mean
between
this one?
10, I cannot see.
Sorry.
So the region between 10 hertz and a couple hundreds, yes.
Why is the worst one? That's the best one. I
The
mean,
thermal noise, no, yeah, it's the best place, but the comparison between the
I see. The increasement in the sensitivity is not so much as in the other cases. That's
I mean, there's a small gap between the LIGO, the black line, and the dashed line. And the place where it's worse is between 10 hertz and a couple.
So is this plot or is it?
Yeah, it's that plot.
Okay. So what you have to compare here is this black line with this one.
Yeah. No, I mean the theoretical the theoretical noises and the LIGO modes. So the black lines and the dashed color.
So the
line.
dash color are the different contribution of a single type of noise.
Yes.
Okay. So the cumulative noise that you have is this one, is the black one.
Okay. Okay.
Okay.
Okay. Okay. Okay. Okay. Now I got it. Okay. Thank you.
You're welcome.
Okay, there's another question there. Well, not anymore. Okay, you guys are ready at the same time, so
Can you explain again the blue lines in the sky plots you showed, where there are also the
The
red
blue
crosses?
line in the sky plot. Okay, let's see. The localization.
Localization
Yeah.
plots.
Yeah. It wasn't there. No, that's not the plot of the localization. It's the plot to explain how the triangulation is done. So this one you mean that you cannot see, of course. Okay,
No.
is this one that you are referring to?
no. I think it's
No.
the one with the blue ellipses. Is that the one? And the blind spots.
Okay. Let's see if I can see. I don't remember.
Yeah,
Okay.
these ones.
Sorry,
yeah.
what is the question again?
I didn't understand what the blue ellipses mean. Like,
Okay, so here we are taking into account 3 initial detectors. So M for Gravitational, the one that you see here, okay, with their initial sensitivity. And what this plot shows is the localization and the associated error region to the source that you will see in that particular part of the sky. So these elongated regions are the error that will be associated to a source that you see in this point, for example. Do you see the mouse? Yeah. Okay. And this is order of, in this case, the detection was 1,000 square degrees. Okay. If from the initial sensitivity curve you go to the advanced one, you gain something in the localization. You see, if I go back and forth, these elongated shapes are a bit smaller. So it would be order of 100 square degrees. Still a lot, but a bit improved compared with the previous one. And if you add, and you see in this case, you have, again, the three detector, they are exactly the same. If you add one detector to the network, so you have also Lego India, that is this one right here, these error regions associated with the source localization will squeeze even more. Okay, so it's just showing you that if we are in a network with a lot more detectors with comparable sensitivity, we can give our result with the error region that is extremely appealing. Let's put it this way. Not at the level of the telescopes yet, but a good improvement.
So on the previous plot before this one,
Yeah.
so in some regions there it's much worse, some regions are better, right?
Yeah.
Where in this plot was 170817? Because it must be somewhere not too bad. I mean, it cannot be in a blind spot, right?
Okay. Huh.
Or, okay, it's okay. If you don't remember, that's fine.
No, I don't remember it. So it was here. Yeah. Okay.
Okay,
Yeah, but
right.
the error region that you have to take into account are these one that are order of tens of square degrees. That's the error region associated with that type of event. Thanks, Ricardo.
I'm curious about why haven't you said anything about Lisa compared to
Yeah, matter of times. You're right. So Lisa is really going into the future. There was the Lisa Pathfinder that was really an extreme success. Um, and so the detector will probably, as we discussed with another student yesterday, will already be able to detect continuous waves in the first operation. The point is related to the uncertainty of the time scale that we have. So we don't. I know that they are hardly working on the detector, but the due to date is not there yet, and so that's why I didn't mention it. But you're right. I have it included in the presentation. Thanks.
Hi, thank
Hi.
you. Well, I have two questions. Have you heard about the MIGA project in France? And do you think this will get better results as their proposal is in an underground facility and they use atomic interferometers?
No, I didn't hear about it. Sorry, I'm not up to date with this. And what is the technology that they are going to use?
Oh, well, I'm not really much of this topic. It's my advisors who works there. It's the LSBB. It's an underground facility of low noise laboratory, and they propose to do a detector, but based on atomic interferometers.
Okay, I see.
And they are building
I
right
didn't
now.
know. So they already have a timeline for the construction, or
The
they are
construction
already?
started in 2018.
Ah, good. Okay. Thanks. I didn't know that.
Okay, one last question here before we break.
Okay, so we do not have the LIGO by
Yeah.
India, but we have now Kagra.
Yeah.
Do we have the same plot?
About the same. Yeah. You have to consider that the discrimination is the arm length. So it's like as adding two will go in the same configuration, but the result is almost the same. 10 square degrees. Yeah.